Hi guys, and welcome to today's video. We have seen already within the Cortex-M interrupt priority video that we can configure the priority of each interrupt line separately via the NVIC interrupt priority register, and that we can have a dedicated 8 bits or 1 byte for each interrupt line. Hence, we can have up to 255 priority levels. However, within our today's video, we'll see that not all those 8 bits can be programmable. Hence, we cannot have 255 priority levels. We'll see as part of this video how we can define what is called priority split point to define which parts are programmable and which are not programmable within our priority fields. And we will see how we can determine within our microcontroller division how many priority bits actually available or implemented for our use case. And we'll finalize our video by a demo running on STM32 microcontroller. So guys, this is our interrupt priority register, and as you can see, we don't have a single register but set of registers to cover all interrupt lines supported by our device. Those registers are part of our NVIC controller. Now, each 8 bits or 1 byte is used to program the interrupt line priority. And we can program the interrupt lines priority separately, as you can see, because we have a dedicated 1 byte for each interrupt line priority. However, what we need to know is that not all 8 bits are programmable. Hence, for certain devices, we will have set of priority bits that are implemented and another one that are not implemented. And we'll have kind of split point to distinguish between the number of priority bits that are implemented within our device and the ones that are not implemented. We'll know in the further slides and also in our demo how we determine basically the split point, and to be more precise, how we determine how many priority bits are supported within our microcontroller device. So guys, the number of priority bits will define how many priority levels supported by our devices. In most of the cases or in most of the devices, we cannot have up to 255 priority levels supported. Some devices, for instance, they define 8 priority levels. Some other define 16 priority levels. For example, here they are 16, not 8. So this is a mistake from my side. So this gets fixed. And those priority levels, of course, they will define how many bits needed to encode those priority levels. For 8 priority levels, we need 3 bits. 2 power 3, this is 8. For 16 priority levels, we need 4 bits. 2 power 4 will be 16. Therefore, those 8 bits, part of this interrupt priority register, are not fully programmable. We'll have a part that is not implemented, and the other part will be implemented and defining basically how many priority levels supported by our device. We need to recognize basically what is called split point, that is separating basically the number of implemented priority bits and the bits that are not implemented. And we'll see how we can determine basically this split point. So guys, this is our Keil-MDK project, and as you can see, this is a C-based project that has been compiled for our ARM Cortex-M based platform. The platform in use is just an STM32 microcontroller, and the project has been compiled and loaded into the flash memory of our STM32 microcontroller. Right now we have already started a Keil-MDK debug session. The program itself consists of using those 2 interrupt lines, line number 0 and line number 1. This one is matching the window watchdog timer interrupt line, and this one is matching the PFD one. And then we try to play a little bit with the priority level of our window watchdog timer interrupt line. However, before even we start touching and reconfiguring the priority level for any interrupt line, we need properly define this global macro. Now this define is used by the CMSS header to have those functions properly working. So those ones, the CMSS macro that they are accessing the different NVIC registers and use it, for instance, to define the priority level of each interrupt line. They rely basically on this global define to know which bits they can write to it. Hence, you need to properly basically define this macro and specify how many priority bits are implemented really. Now, to really know how many priority bits are implemented, we need just to go to the base address of one of those interrupt priority registers within our NVIC block. So this base address, this is the base address for our interrupt priority register number 0, E000, E400. and then we'll try to program the first byte that is matching the interrupt priority number 0. Then we try to write with FF, and here we go. As you can see, we can just write to the first 4 bits MSB, or the 4 MSB bits, as you can see. In general, as stated before, we cannot have the support of 255 priority levels. In most of the cases, we'll have some bits are implemented and use it to define the different priority levels, and some bits are not implemented. When we are saying 4 bits, 5 bits, or 6 bits priority bits, we are meaning basically the MSB ones, not the LSBs. So if we have 5 bits priority bits, then means let's say the 5 MSB bits are the ones that are implemented and we can write with, and the LSB 3 bits are not writable. If we are saying that we have 4 bits priority bits, or to define the different priority levels, means the 4 MSB bits, not the 4 LSB bits. As you can see here, we have tried to write FF, and we are able to write only to the 4 MSB bits. The other ones are not implemented. Hence, we need to create or invoke basically this define and specify the value 4. Then we can compile our code, and hence those APIs, and to be more precise, the set priority API, part of our CMSS header, will rely on this global define to properly know which bits it can write to it. And hence, if we say 1, then it tries to write to this, or to those 4 MSB bits, not to here. If we specify 2, then it knows where to put 2, here, not here, and so on. With this easy trick, we can recognize basically our split point to determine how many bits used to define the different priority levels within our ARM Cortex-M microprocessor.